I was like a little bit.
Those of you who have been here before, welcome back. And for those of you who this is something new, we do this every Friday where we have speakers from other academic institutions or industry or whatever, talking a pretty wide variety of topics. Hopefully you'll enjoy them. But if you do have some other ideas or suggestions for future topics, please let me know. So today we have a special guest, Dr. Fukuda. He's from the University of Tokyo, where he also received his PhD degree. After receiving his degree, he worked at Yamagata University as assistant professor and then joined RIKEN. And he is currently a senior research scientist there in the thin film device laboratory and Emergent soft system research team, which we'll hear more about today. His current research interests are organic transistors, flexible electronics, and printed electronics. So I think many of you are interested in that topic and doing perhaps some research in that area. So we welcome Dr. Fukuda today, and I'll turn it over to you.
Thank you very much, John, for your kind introduction. Hello, everyone. My name is Kenjiro Fukuda. I'm very happy to be here. This is the first time for me to visit UC Berkeley. I'm very excited to see the very beautiful buildings, the towers. And then today I would like to talk about the very thin, stretchable organic solar cells, photovoltaics, and photodetectors, and other applications, integrated device systems. I'm the Kenjiro Fukuda from RIKEN Takao Someya Research Group. The Takao is managing two research groups. The one is in the University of Tokyo. The other is RIKEN. RIKEN is not a university, but the National Research Institute. Most members are postdocs or senior researchers, and I'm the kind of a senior research scientist in the Takao Someya Research Group. And before starting my talk, I would like to thank Theo for arranging everything. Because when I visit UC Berkeley, I send a message to Theo because he is now in the Ali Javi's group as a visiting student. Then he kindly arranged to have a seminar for me, and this is a very good opportunity for me to be here and have a seminar for you. Okay. Then I would like to start my presentation. The target application is kind of the wearable, very, very thin, very, very flexible, or gas permeable sensor systems, wearable application systems, as shown here, like that. The very thin sensors adhered onto the human skin directly. Then such as sensors that can monitor the vital signals continuously for long terms. Then normally the Tokyo Takao Someya teams is focusing more on sensors. For example, Theo is focusing on the sensor devices using photodetector, organic photodetectors. And then so RIKEN Someya team is more focusing on the power sources because every electronic devices need electricity, the power sources. So we are focusing on the solar cells to generate the power to supply to make integrated systems. Okay. Then we are more focusing on how to make very, very thin electronic device systems. Then here I would like to show you the very important equation, the flexural rigidity, to explain why thinness is very important parameters. Here, flexural rigidity D is determined by using these equations. The E is the Young's modulus of the material. T is the thickness of the films. So you can easily understand if we reduce the thickness, then it can be more effective to reduce the flexible rigidity values. So that we try to reduce the thickness of the whole device systems to make more softer device systems. This concept was clearly proven by Professor Dahyun Kim and John Rogers previously, almost 15 years before. Dahyun fabricated this inorganic based TFT systems onto the polyimide films, plastic films. When they use the 76 micron, the thick polyimide films, there is a poor contact between the device and the brain surface models. But when they decrease the thickness of the film than just a substrate, down to 2.5 micron, they could make a very good contact between the devices and the brain surfaces. Because the flexural rigidity is dramatically reduced, that devices can be easily bent, as shown here, then it conform to the wrinkled surfaces. This is the kind of the very important aspect why we need to reduce the thickness of the devices. Then we are focusing on very, very thin organic solar cell systems. As you here, this photo shows our solar cell modules fabricated onto the 1 micron thick polymer substrate. The features are very flexible, very lightweight. Then the very thin properties. The specific number is 3 to 4 micrometers, including substrates and passivation layers. The total thickness is just 3 to 4 micrometers. And then thanks to such a very thin properties, we could achieve the highly robustness for the bending mechanical stresses. And then another important aspect is very large power per unit weight of the solar cell devices. Specific value is 40 watts per gram. If we prepare the 1 gram solar cells, then that can generate 40 watts under the strong one-sun light illumination. This is kind of the amazing values. Okay, then this large power per weight is proven by many research groups in the world. The left shows the organic PV cases reported by the Professor Hongchen Chen, Zhejiang University, China. In their studies, they achieved a power conversion efficiency of 17.3%. Then they reached the power per weight value of 39.7, almost 40 watts per gram. For perovskite cases, the Martin Accountant Brunner from JKU, Austria, achieved a PC of the 20.1%, and then the power per weight value of the 44 watts per gram. And then they put such a very thin perovskite solar cell onto the drone surfaces to make the power supply system for the drone system. So because these very thin solar cells have the lightweight properties, this can be very beneficial for such a robot application that requires lightweight properties. So this is the one very good examples of the application using very thin solar cells. Okay, then here I would like to show you the structures of the OBBs, the devices. We normally use the 5 functional layers. The first is the transparent electrodes, then the electron transport layers, then active layers. Normally we are using the donor acceptor, the organic material blend systems. This is the photo absorbing layers. Then the whole transport layer. The last layer is the top electrodes. Normally we are using the opaque silver electrodes. So we could make the non-transparent organic solar cell systems. But if we replace opaque electrodes with transparent electrodes as the top, then we could make the semi-transparent OBB systems. Then important layers besides these 5 functional layers are substrates and passivation layer or superstrate. So normally the normal flexible organic solar cell researchers use the 100 micron thick, the polymer substrate, such as the 100 micron thick PET substrate, PEM substrate, transparent polyimide substrate. But we are using 1 micron thick substrate, the other substrate, and 1 micron thick the passivation layers to make the total thickness of the around 3 to 4 micrometers. Okay, then here I show the summary of our recent achievements. We are focusing on how to increase the power conversion efficiency of organic solar cells and how to improve the stability of the devices. And then we try to focus on the high throughput fabrication processes, more specifically the solution processes to make the devices. then the application, how to integrate each system, such as the power sources, sensors, all together to make a wearable systems and the soft robot applications. So I would like to show our progresses one by one. The first topic is high power conversion efficiency and output powers. Okay. Here I made a summary table or figure showing the PCE, the improvement history in the world. I plotted the three different colors conditions. The black shows the rigid certified PCE of the organic solar cells. The recent, the world best OPV solar cell reached the over 19%. Then and then these blue curves show the normal flexible organic solar cells. And then this red curve that shows the very, very thin, ultra thin organic solar cells. Typical thickness is less than 10 micrometers. And then this star plot represent our studies. Recently, the PCE using a very thin substrate was reported by the Zhejiang University research group. So currently, we are not the best. Unfortunately, we are trying to be the best again. But anyway, the recent researches improved the PCE of both flexible and the ultra flexible organic solar devices dramatically. So from less than 10% to around 17%. So dramatical improvement could be achieved within these 10 years. Okay. Then an important aspect is materials. Because the organic electronic devices could be improved the performances by using the newly synthesized organic materials. So recently we are having the collaboration with organic chemistry researchers in Chinese group. Then we received a very good organic donor acceptor materials from their groups. Then we fabricated a very, very thin organic solar cell devices as shown here, and we could achieve the high PCE values up to the 17.8%. This is now our postdoc is now preparing a manuscript. So then I hope that this value will be plotted in the previous figure soon in the future. And for solar cell cases, both PCE and actual power output are very important. For aiming the high PCE, we normally make very small cells. For these cases, we fabricated a 2x2 millimeter solar cell to achieve these values. But for the practical cases, of course, we need a large area modules to make a larger power output. So now we are trying to make a little bit large modules. That we have the Japanese company to ask to make this kind of mini module system using our very, very thin substrate films. And then they could fabricate this kind of 10 by 10 square centimeter very thin solar cell system by themselves, their companies. Then in these device modules, the effective area is the 43 square centimeters. And the total output, it reaches the 130 milliwatt under the one sun illumination outdoor conditions. So 100 milliwatt is enough large to drive most electronic devices, wearable device system. So of course, there are a lot of room to be improved in these modules because when we calculate the PCE, the PCE is just around 3% in these cases. So there is a huge gap between 3% and 17%. So maybe the process engineering makes the much improved performances of the module, very, very thin modules.
At what voltage are you getting your max?
At
which voltage are you getting your maximum?
Around here. Sorry, I forgot when is the actual values, but here it should be the MPP points. Okay. You can see that fill factor is not good. If you're familiar with solar cells, so maybe there should be some leakage values behind the fabrication of the modules. So maybe this should be improved later. This is just fabricated maybe last week, last month. Sorry. So still unpublished works. Okay, then recently we are more focusing on the stability improvement because we cannot use the very good gas barrier layers for our very thin solar cell system, and normally organic devices are sensitive to the ambient air conditions. So how to improve the stability is very important issue for practical application of our solar cells. So recently, we achieved much improved water stability of the organic solar cell, so that our solar cells could be operated underwater, as shown here. This is reported by our postdoc, Sushin, last year. Then the main finding, important technical achievement is to change the whole transport layer from the water sensitive normal materials to the normal insensitive ones. The more specifically, we use thermally grown silver oxide layers as HTL materials. And we deposited the silver directly onto the active layer surfaces because there is no HTL, full transport layer. The initial as-grown device shows very poor performances. As shown here, this black curve, the performance PC is just 0.2 something, almost no solar cell performances. But after annealing of the devices in the ambient air for 24 hours, improved the performance dramatically from 0.2 to 14, around 14%. Dramatical improvement could be observed because of the generated silver oxide interfaces. Okay. Then the new HCl is very beneficial to improve the water stability because normally we are using the water sensitive HCl such as PEDOT-PSS or molybdenum oxides. Both are very water sensitive. Silver oxide is not sensitive to the water. So this is proof of the water stability in comparison with the existing normal HCl systems. So orange curve shows our newly developed systems. Gray curves shows our conventional molybdenum oxide silver system. You can see the much improved water stability when using the silver oxide silver systems. Even after 60 minutes dipping into the water, the solar cell could be operated underwater almost normally. So this can be of course beneficial for the many kind of the applications because when we focus on the wearable applications, we can easily expect the water, the adhesion onto the device surfaces, such as today's rainy day. When we walk around, we can easily get the waters onto the device surfaces. Then we could avoid the degradations and such a rainy conditions or high humid conditions. Okay. Then we are slightly modifying these technologies to improve the water stability further of the not only organic solar cells, but also the organic photodetectors. Because the organic photodetectors have the almost same structure as organic photovoltaics, we could fabricate both solar cells and photodetectors with the same processes. And in this study, we added the elastomers. The more specific name is SEVS, SEVS, into the active layer material to make the adhesive, sticky interfaces between the active layers and the bottom, the interface layer and top interface layers to make the more water robust photodetector systems. And here is showing the adhesion force mapping of the active layer without and with SEVS, the elastomers. And you can see the adhesion force is sharply increased when cells was added to the active layer surfaces. So these partially increased adhesion forces beneficially improve the water stability. Okay. Then here we showed this kind of demonstration. We adhered our photo detectors onto the human skin, and we dipped such devices underwater, and we applied the light illumination with the inorganic LEDs from the nail side, and we see the heartbeat rate using these kind of systems, because when the blood pulse goes through the skin, the wave signals can be changed according to this blood volumes. And then here is the actual obtained results as a function of the time. Then you can see the kind of the heartbeat signals from these kind of systems. The important result in this study is the waterproof properties of the self-added active layer systems. So when we use the self-added photodetector devices, our devices could be operated underwater even after 5 hours immersing. So this dramatical improvement could be beneficial for the kind of the water containing the sensing situations. Maybe the easily we can imagine the one practical application for kind of swimming the sensing applications, because the swimming needs of course the waterproof properties of the whole device systems. Okay, so this kind of waterproof, water stability improvement is recent our achievement. Okay, then I would like to move to the integrated systems, and the interaction technologies, how to make the integrated devices. This is very important aspect. And here we draw these images as the future self-powered wearable systems. So we are focusing on the solar cells, but of course there are other energy harvesting technologies such as TANG or the thermal generating system and so on. So these power sources, energy harvesting systems, it could be merged into the one wearable device systems, and then generate the power. And there should be the batteries. Then such a batteries will operate the electronic device systems, the sensor systems, the actuators, tactile sensing, and so on, to make the one meaningful application system. So how to make the integrated system is very important challenge for us. So here in this study, we are focusing on how to make the conductive bonding between different, very, very thin electronic device systems. Because if previous studies, we normally use the wires, just the wires. I'm not sure whether it is correct English name. We are using the alligator clips to make the connection between the one device and the other devices. Of course, such a wires is not so flexible in comparison with our very, very thin solar cells or LEDs. So we try to solve these problems by using non-adhesive conductive bonding technologies. More specifically, we could achieve gold direct bonding system using the plasma treatments. And here I show the OPBs driven OLEDs, the device integrated systems. These two devices are connected with these gold films without any conductive adhesion materials. And then here I show the more details of the processes. The process is very simple. We prepare the two gold films onto the very, very thin substrates. In this case, we use the pyridine as the polymer substrate. And then we apply the aqua plasma, the water vapor plasma onto the gold surfaces to activate two gold surfaces. And then after that, we overlap these two gold layers. And then we store this overlapped gold in the ambient air conditions, room temperature for several hours, maybe 12 hours, maybe the smaller storage time should be okay, but we stored for around a half day to make a perfect bonding. And then here, this right shows the XPS analysis of the gold surfaces before and after the water vapor treatment. When we apply the water vapor plasma, this kind of the OH group related signals are generated on the surface of the gold. So we expect that the OH group can help to make the bondings. And here is the proof of the direct, almost perfect bonding at the interfaces of the gold and the gold. We separately fabricated gold, and then we did this kind of bonding technologies, and then we see almost the perfect bondings. Here is interfaces having almost no color changes, no contrast. And here, number 1 point, you can see the colored interfaces regions. So these regions implies there was an interface. But anyway, we could make almost perfect bonding with these simple processes. And then here, this number 1 region shows a little bit higher oxygen amount. So we guesses. Firstly, such an OH bonding makes the OH weaker bondings at the interfaces. Then later, such a OH bondings can be replaced with metal bondings, the gold-gold bondings, to make the stronger bonding interfaces. And then here, we added the other metal bonding systems. The top shows silver bondings. And the bottom is silver gold bondings. These kind of the other metals or different metal bondings also could be achieved with water vapor plasma technologies. So this should be very beneficial for the integrated systems. And then this movie shows the demonstration that our bonding can operate the integrated systems perfectly. Here, we made these integrated systems with the direct bonding system. Because the wiring is enough flexible, we could make the crumpling of wiring and OLEDs simultaneously. Even after that, the integrated systems could operate perfectly normally, as shown here. Okay. Then we recently tried to make the meaningful systems. So in this study, we integrated the pyridine gold, the wiring with silicon-based strain sensors. In this study, that we had a collaboration with Professor Takamatsu in University of Tokyo. Recently, he moved to New York. I forgot which university, the university name, but he's in the US. And then they fabricated very, very thin silicon-based sensors having a 5-micron thicknesses. So we added the gold, the evaporated gold, onto the silicon strain sensor surfaces, and we applied the water vapor plasma to make the bondings of the silicon sensors and the pyridine films. And we could achieve the perfect bonding of such a different substrates interfaces. And then this is the TEM observation. The bonding interfaces is almost there is almost no interfaces from the TEM images. The two lesions are almost merged, fused, as shown here. So we could achieve this direct gold bonding system for different substrates. And then the important benefit is that we don't use any adhesives. So there is no relaxation of the strain sensors. So if we use the adhesives, the strain sensors was relaxed. So the signal is changed. But if there is no adhesion, such a drift is not observed. So this is very, very important aspect when considering the practical applications of the strain sensors for example, real application. Oh, do you have any question?
Yeah, so this is really, really cool, by the way. So when we do gold bonding for normal stiff solid silicon wafers, they don't stick usually because there's just a little kind of oxidation. What the type of oxidation on your layers are, you use gold, which doesn't oxidize, but silver does. And then you also know what the effect of the flexible substrate class.
Okay, then both are very good questions. For oxidation points, we tried to use the oxygen plasma treatment to make the direct bonding, but we failed. So water vapor plasma is very important technology. So I'm not sure whether you can have the access to use the water vapor, but oxidation should be avoided to make the bondings.
Oh, but water vapor is
Not oxidized. So normally this causes the re-oxidation because the H, the gases, it could be generated inside the chamber. So this then make the de-oxidation instead of the oxidation. Okay.
even though there's still oxygen.
Yeah.
That is cool. Okay, and then does the thickness of the substrate affect how good the bond is?
I think the thickness affect the bonding properties. But I'm sorry that we haven't tested the thickness dependencies yet before. So maybe the 10 micron should be okay. For our cases, 1 or 2 micron parent substrates are used, and the silicon is 5 micron. These thickness ranges are okay. 10 micron should be okay, but over 10 micron, maybe the bonding strength it should be decreased. Okay, then we show that this kind of real shopping demonstrations. Yeah. Okay. If the adhesion is used when we grab the items, when we hold such a grabbed items, the strain sensors gradually relax. So maybe this demonstration will fail. Yeah, the items will be dropped. We succeeded with such a direct bonding systems. Okay, so this kind of integrated system should be very important. Okay. Okay, then we are next topic is how to make the solution processes for integrated systems. So we are focusing on the solution processes to make the photo devices, more specifically the OPDs, and OLED devices. And then in this study, we eliminated both HDL and EDL from these photo devices. We fabricated very simple 3 structures, 3 layers, transparent electrodes, active layer directly, and then again the top electrodes directly. All these 3 layers are fabricated using the solution processes, the blade coating or spray coating. And then we just simply change the active layer materials, the PM6, Y6, IT4F for the OPDs, the P3HP, PCM systems for OPDs, and the super yellow for OLEDs. And then the E-gain, PSS, these 2 electrodes are used for all different photo devices. And then important finding is how to make the uniform films of the E-gain onto the active layer surfaces. Normally, the E-gain liquid metal has a kind of the non-wetting properties onto the active layer surfaces. But we found when we sprayed the E-gain in the ambient air conditions, we could make the very uniform films onto the active layer surfaces, as you here. And then we did the observed and we did the simulations to confirm the wettability differences in the different ambient conditions. When we dropped in the nitrogen conditions, there is no oxidation on the surface of the E-gain, so the wettability was poor. But when we dropped the E-gain in the ambient air conditions, the surface of the EGAN was oxidized quickly. Then such an oxidation, oxidized layers helps to make a uniform wet the dropped films as shown here. This was also confirmed by the console simulation as shown here. So then we could fabricate the 3 different photonic devices using the full solution processes. And we obtain a reasonable performance, not the best, but reasonable to make the integrated systems. OPBs works normally. OPD maybe okay. OLED the performance is not so good, but anyway, we could see the light illumination of the OLED devices using these 3-layered solution processes. Then finally, we integrated 3 different devices to make the self-power wearable PPG sensor systems. So we generate the power using the solar cell modules to supply the power to OPDs and the OLEDs. And then LED light, illuminated and go to the skins and reflected, and we detect such a reflected light signals using the OPDs. And then we succeeded to see the heartbeat signals using these kind of integrated systems. And an important point achievement is the storage stability in ambient air conditions. Even after the 1 month, the storage in the ambient air conditions, our integrated systems could be operated almost normally. You can see the small noises in the aged devices, but still we could see the heartbeat signals from these aged devices. So this means our solution process devices can be stored in the ambient air conditions. So maybe this can be useful for the practical applications. So we don't need the glow box systems to store the devices. Okay, then recently we are trying to focus on the different applications, and we are more focusing on the integration with soft robot systems, soft actuators. And here we show the integrated system of the OPDs with DEA, dielectric elastomer actuators, DES. And then the DEA researchers integrated our solar cells to make these kind of systems, and these kind of swimming robot system driven by DEA could be achieved with the very, very thin organic solar cell systems. And then finally, I would like to show you another example of the soft robot integrated systems using the living insects. So the purpose of such a living insect usage, the cyborg insect approach, is the kind of the disaster rescue tasks. So when the disaster occurs, the big earthquake occurs in the cities, we have to seek the people under the kind of the buildings. In this system, in these cases, of course, the human is very dangerous. So human is not good. The robot system is better, but the normal robots are very big, so they can't go through under the rubble. So very, very mini robot system is required for such a rescue tasks. But the normal robots require a very, very high energy consumption. The typical value is around 100 milliwatt to make a kind of a locomotion. If we use the living insects, the power consumption is much reduced to less than 1 milliwatt. Typical value is just 100 microwatt because the locomotion actuation was generated by the living systems. And we could make the control of the living insects by using the electric signals. Okay. Then we need to consider what's the energy charging systems reported so far. The left is using silicon-based solar cells directly adhered onto the insect surfaces. Of course, this is very heavy, bulky. This is not good at all for the insects. And then right shows the kind of the biofuel cell approaches. in this study, the Professor Morishima group in the Osaka University, they really achieved the recharging systems using their biofuel cells, but still the system is very heavy, bulky. So then we got the idea to use our solar cells for such a rechargeable cyber insect system. Then here is our devices. I'm sorry, this is a very rigid, bulky systems. This is the kind of locomotion control systems. The achievement is here. Our solar cells adhere onto the insect abdominal surfaces. And I'm not sure whether you are familiar with Japanese cultures. One student went to the Akihabara Otaku town to buy these circuits by himself, and he integrated these systems by himself in this study. Actually, these systems should be miniaturized when the mature company prepare the silicon-based technologies. This can be miniaturized, but a solar cell should be thin and enough large to make enough powers. So we put solar cells onto the body surfaces, and here is the setup of the circuits. We made a wireless motion control systems, and then we generate the stimulation signals, and then we apply such an electrical signal to sensory nerves of the insect bodies. And then here is the solar cells. When the solar cell generate the power, the voltage is increased from around 1 volt to 4.2 volt using a boosting converter. And then this increased power is charged to charge the lithium polymer batteries. This is the whole system. So in this study, we use the commercial lithium polymer batteries to make the whole systems. And an important point is how to adhere our very, very thin solar cell film-based electronics onto the abdomen surfaces. If you are familiar with the insect bodies, you understand that insects, the abdomen has multiple segments, the 8 to 9 segments in this insect. And then we should keep the freedom of such a segment movement when we adhere the films onto the abdominal surfaces. So we applied the adhesion, non-adhesion, interleaving structures to make a freedom of the movement of the segments of the insect bodies. Okay, when the segments are overlapped, we see the thin film, our very thin films are bent outward, as shown here. Then this can make the freedom of the motion of the insect bodies. Okay, then here shows how much the very thin film adhesion is beneficial for the motion abilities. Left shows no film. The insects can quickly traverse the obstacles. If the abdomen is fixed, it takes very long time to traverse the obstacles. And then if we use the 3-micron films, this can make no changes of the traversing speed. So here is the result. There is almost no differences between without films and with 3-micron films. This is very beneficial to keep the basic motion abilities of the insects. And then the trial is the kind of the self-writing attempt. Here, these top 3 movies shows the attempts of the self-writing, the upside down attempt with no film, 5-micron film, and 20-micron films. With no film, they quickly succeed. 5-micron, it takes time, but finally they succeed. 20-micron, they cannot. We people, human, they almost don't recognize the differences between 3-micron, 5-micron, and 20 microns. Both are very enough thin for us. But for them, this is very critical differences. And then fortunately, our solar cell have the 4-micron thick. So they succeeded, almost 100% the attempt, they succeeded. Here is the summary. You can see the clear, very clear differences, thickness dependencies of the writing success rate. Okay. Then we try to change to describe more physically using this kind of buckling load models. Okay. Then here we replot the success rate as a function of the buckling load with different film materials and different thicknesses. And you can see that there is a very good relation between the buckling load and writing success rate with different materials. The more the harder pyridine and softer PDMS both shows the almost similar threshold values around the 0.1 Newton. And then this is very good to apply these kinds of approaches for other soft robot actuator systems because many insects have the similar segment movement systems. So if we consider these kind of similar soft robot systems, this can be fully applied. The important parameter should be buckling load. Then what is the threshold values we determine, then we prepare the good enough appropriate the thinness or softness as for the flexible devices. In these cases, 5-micron pyridine or transparent polyimide, the substrate films are enough for these cases. Then this is the final demonstration. We integrated all systems together. Then when the battery is empty, we could not do any locomotion controls. And we applied the sunlight illumination to the living insect bodies for several minutes, 30 minutes. And after charging, we could do this kind of wireless motion controls. Okay. Actually, it looks very funny. And you think I'm the crazy guy, but actually I'm not the crazy guy. This cyborg insect project is mainly led by Professor Sato in the Nanyang Technological University, NTU. So their group is focusing almost 100% effort to make this kind of integrated systems because they received a lot of big funding from the Singapore government. And so they really wants to achieve these kind of systems. And I helped their projects using the Marvel solar cells. And I hope in the future that these kind of integrated system will be further improved and then make our actual practical system integrated cyborg insect system for the rescue task or any other applications. Okay, here's the summary of my talk. I mainly focus on the solar cells, but I'm focusing on the other aspects such as integration technologies to make the actual integrated system for meaningful applications. Okay. I would like to thank all collaborators, all lab members and the collaborators shown here. And thank you very much for your kind attention.
Hey, question? Yeah.
Thank you for the excellent talk. How do you fabricate the solar cells?
Normally, we are using actually, if you're familiar with the organic solar cell fabrication, they simply answer the fabrication process is almost same as the rigid organic solar cells. The different point is just we use, first we prepared very thin films and we deposited ITO directly onto the substrate and we did the photolithography process to make the patterned ITOs. And the remaining process is same. We use the spin coating processes or vacuum evaporating techniques to make the metal formation.
How do you do this spin coating kind of operation with the substrate? How do you handle it?
Sorry.
How do you handle the substrate when it's so?
Yeah, this is very good question. So because this is very difficult to handle freestanding films, so we first adhere the films onto the rigid support. Normally we use the glass, the support, to fix. Then after the fabrication processes, we peel the devices, the whole devices from the supporting plate. So at the interfaces, we form the kind of releasing layers. Normally we are using the hydrophobic the materials, the fluorinated the polymer layers on the glass support plate. Then we form the very thin substrate films. Then these interfaces is okay for the fabrication. The devices are normally not peeled during the fabrication, but after that, we cut the edge, then the peel. Then we could make the freestanding film devices. Okay.
Very impressive talk, and I have a question about you mentioned that you will focus on ultra thin solar cells and use wearable electronics. So my question is that very important about you need such thin layers? Because for the sensors, you need ultra thin because you can attach to our skin and collect the more accurate data. But for the solar cell, it looks like it's just like energy supply.
Yeah.
So even you use maybe a little bit thicker, the solar sensing, the solar cells still can work, right?
Yes, you're.
Could you repeat the question for people online?
Okay. He asked about the necessity of the thinness, whether we need such a thin organic solar cell.
Yeah.
Maybe the kind of the specific answer is the cyborg insect project. Because you are almost right. For the wearable systems, the normal thickness, maybe 100 micron should be a little bit too much. But around the 20 micron, 10 micron, this should be okay for the wearable applications when the solar cells are adhered onto the textiles, the clothing. But when we consider the extreme cases, for example, the very soft robot system or drone systems, lightweight properties should be more important than such a textile system. So that's why we are now focusing on the applications, the aspects more, because this is kind of the open question whether we need such a very thin solar cells. The thin properties sacrifice the stability. It's true. So we need to find appropriate the thickness for each target application.